Hi guys, this video is about enumerated types and switch statements in C, and I will motivate these two language features with our compiler project, how we can use them to improve the implementation of our Lexer. This is the declaration of function getToken in the header of the Lexer. It returns an integer value, and currently 0 means the end of input is reached, 1 means a bad token is found, and so on. And we just specify these meanings of certain values in the comment next to this declaration. And hopefully this comment and this meaning that we communicate to users of this function is consistent with the implementation. Here we actually have to make sure that 0 means the end of input is reached and 1 a bad token was found. Now let's assume that we change the implementation of the Lexer so that from now on 1 means the end of input is reached and 0 means a bad token was found. Then we should not forget to update this header, because in other places this function gets used and maybe by others. Then these users of this function need also to read, of course, this header and this comment, and then from that use the information to adapt their implementation so that the program works again correctly. So this is inconvenient, first of all, but also error-prone. And it's error-prone because we are doing, in this case, bookkeeping just with comments. And in this case, actually, the compiler can do exactly the same bookkeeping for us in a more reliable way. Before I actually show you my suggested solution where the compiler is doing the bookkeeping for us, let me show you another solution. What we want to actually have are meaningful names, meaningful identifiers for certain integer literals. And of course, we could just define some macros. That means we would use the preprocessor for doing the job. The preprocessor would replace all these identifiers with this integer literals. And that means before the compiler actually sees any code, all these symbols already are replaced. So the compiler would just see the code from before. And the problem is solved because if we change these definitions, this change takes effect everywhere where these identifiers are used, as long as they are used after these directives are seen by the preprocessor, of course. The problem is, actually there are many problems. One problem is that you would, for example, get strange error messages in general, because the compiler in this example would see that this 0 is used as a name, an identifier for a variable, and this variable should be initialized with 42. Well, nowadays, of course, the preprocessors are usually deeply integrated into the compilers, and then you get better error messages compared to a few years ago or a few decades ago. But there are other problems related to macros. You probably know that from this video about the preprocessor, and there is actually a better solution to this, some solution that is part of the C programming language. For having meaningful identifiers for certain integer literals, you also can use these enumerated types in C. And in this example, you see such a type definition, where in this curly parenthesis, you have a list of identifiers. And in this example, the compiler will assign to this first identifier the value 0, to the next the value 1, and so on. So counting begins at 0 and the compiler counts by 1. It's important to understand that you're not defining here some variables that have some initial value. So there is no data generated for the data segment or BSS segment or the text segment. This mapping of identifiers to certain integer literals is usually just handled internally by the compiler in its symbol tables. And that means you will have the same effect that you would have with the macros. That basically, if you use these identifiers, it's equivalent to using this plain integer literals. The reason why it's still called a definition and not just a declaration is that a compiler could generate from that some EQ directives. Nowadays, this is usually not the case, but it could be the case. So the term definition and not declaration is correct here. So for using this enum constants, you just use these identifiers in the code. It has the same effect as for the macros. The advantage would be that you would get always more meaningful error messages, because if you use this constants for the name of a variable, the compiler could say this was already defined in line so-and-so as a constant for this enumeration type. And this is actually a big advantage, or one of the big advantages. In the declaration of function getToken, we still use as return type int, which is kind of not expressive because it's not making clear that its return value will be one of these enum constants that we defined above. For making that clear, we will first change this enum type definition by adding a so-called tag to it. And then together with this enum keyword and this tag, you can use this for type declarations, like for the return type of this function. For the implementation of the function, it simply means that we change its return type also here to enum token kind. For the C++ programmer view, there is something you have to obey. In C, you actually have to use enum together with the tag. You cannot simply use the tag name like in C++. I also want to talk about a few pitfalls that you probably would not expect, at least if you're coming from Java. You certainly see how this little example basically reflects our getToken function. It's supposed to just return either the value 0 or 1, because those are the values that we specified above as enumeration constants in this enumeration type definition. But what happens if we by accident would return 42? Would we then get a warning or an error saying that 42 does not fit in a variable of type enum dummy? Well, unfortunately, at least in this case, not. This is perfectly fine C code. In C, enumerated types are just signed integer types. You will see on the website some extract from the C standard that the compilers actually have here some choice what internal type actually will be used, but it could, for example, be int, and then you just can store in such a variable all values that are representable with an int. And that means for us, we have to be careful. We cannot rely on declarations about enum types that values are just one of the listed enumeration constants. So we need to have some error checking in general done by ourselves too. We cannot use the compiler for doing this for us. Sometimes you want that these enumeration constants have some specific value, like in this example properly. Then you can do the following. You can explicitly specify these values, or you also could, in this case, just specify for the first constant explicitly a value. Then for the remaining constants, the rule, by default, the value of a constant is the value of its predecessor plus 1 gives you the same. So here the counting is just done by the compiler. So this is kind of convenient. Now in the next example, you see that it is possible to have different constants with the same value, because I'm resetting the counter after a while to 1. That means I have two constants with the value 1, two constants with the value 2, and so on. Now here, this is probably what I want. But in other cases, like here, I want to make sure, or should be sure, that all these constants do have actually different values. You have to know that if you use this character literals, the value is the ASCII value of this character. So in this case, everything goes well. I have 4 constants. They all have different values. Now, if I reverse the order, I have a problem that I now have 2 constants with the same value. And in this case, this is not what I actually want. So this is just another pitfall. In our compiler project, we will actually provide a new header file for this enumeration type definition. And there we will also declare a mapping function for mapping token kinds to a string representation. And the implementation of this mapping function will use a switch statement instead of this if-else-if construct that we so far used for this purpose, for example, in the test program for the Lexer. Using a switch statement here is much more expressive compared to this if-else-if construct, and more expressive means less error prone, easier to maintain, simply better. And here we also can do this internal error handling. That means the test program simplifies to that we simply call this function before we do the printf. Now, of course, implementing this mapping function for mapping token kinds to string representations is also kind of error prone. Let me show you how we will finally, in the end, solve this problem. There will be one text file with a list of all token kinds, and from that we will generate this header file for the enumeration types, and we will also generate this implementation of this mapping function. And then we can actually deal with that. But first we have to deal with these switch statements and also what kind of pitfalls they offer to us. In our compiler project, we will add a new header file for this enumeration type definition for the token kinds, and we will also provide a function for mapping a token kind to its string representation. This, of course, will simplify the implementation of our test program for the Lexer. We just call this mapping function and print out the result. But it also means that what we before implemented in the test program kind of needs to be implemented in this mapping function. But there we will use a switch statement instead of this if-else-if construct. And compared to this if-else-if construct, this switch statement is more expressive, and more expressive means less error prone, easier to maintain, simply better. But of course, this is still kind of an error prone construct, because if we add a new enumeration constant, we should not forget to add a new case. Let me show you how we will solve this in the end. We will write a program that reads in a file that contains a list with all the token kinds, and from that it will generate this header file, and it also will generate the source file with the implementation of this mapping function. But before we deal with this, how to solve this problem, we first have to consider how to avoid certain other problems related to switch statement, because here C also provides certain pitfalls that we want to avoid. Let me explain with this simple example how a switch statement works typically. A switch statement just has one expression. In this case, it's a simple expression, just this identifier foo. This expression gets evaluated, and then depending on the value, the execution of the program continues after a matching case, if such a matching case exists. In this case, we have two cases, case 1 and case 2. That means if foo has the value 1, execution starts after case 1 with printf foo is 1, or if foo is 2, it prints foo is 2. If foo has a value that is not found in a case, and if you have a default label, then the execution continues after this default label. Here we do have such a default label. It's not required to have that, but it's good practice to always have it, even if this default label just has an empty statement. You also see that in this switch we have these break statements. These are not required, and if such a break statement gets executed, it means that you terminate the switch statement. That means you jump to the end of this switch statement. You also see that in this example, these expressions after this case are always integer constants. This is actually required. So you cannot use here complex expressions or floating point constants or variables. These actually have to be integer constants. This of course also includes character constants. You also have to make sure that these cases are disjoint. That means you cannot have two case 1 labels. So that's actually already it. And now we come to the pitfalls. The most common pitfall is a forgotten break statement inside of a switch statement. Let's change the example so that we know foo has the value 1. That means the program execution continues after this case 1 label with the printf statement, and after that all following statements will be executed until either the end of the switch statement is reached or a break statement gets executed. And a break statement will just go to the end of the switch statement. So if you would remove this break statement, it's not an error. The statement that follows this printf for foo is 1 just would be the printf for foo is 2. So this also gets executed, and then we have a break statement which then terminates the switch statement. So whether you want to have such a fallthrough is kind of a question. Most of the time this is not intended. That's why nowadays compilers will give you a warning. If a case has a statement that follows this case, but then you do not have in this case block also a break statement. And this somehow indicates that most of the time this is not what you want. If you actually want to get rid of these warnings, you have to do something. You have to turn off certain warnings. The next pitfall is about not considering all possible cases in a switch statement. Sometimes you do this on purpose and sometimes accidentally. Like in this example, it could be that you do not know that you also could store the value 42 in this variable foo. And then the switch statement would not handle this case. If you want to express that you on purpose want to ignore such cases, then use a default label with an empty statement like that. That's it for this video. On the website you will of course find more information about these topics and more examples and also an exercise.